Artificial intelligence and machine learning and ChatGPT, all of this stuff is in the news every day, it seems like. All the biggest tech companies behind it are blowing up on the stock market. People the past couple years have been sending me steel compositions that they asked ChatGPT to derive. Can ChatGPT make a new stellar knife steel? Can it be better than anything out there with its amazing artificial intelligence technology? Well, I took a bunch of the knife steels people have been sending me from ChatGPT, and let's analyze them.
Shall we activate the Bat computer?
That sounds like a good idea. Feed it a question about dozens.
This first one, ChatGPT named Infinisteel. So this guy asked ChatGPT for a new super steel, and this is what he got. ChatGPT says, introducing the revolutionary super steel Infinisteel. This cutting-edge material boasts unparalleled toughness, edge retention, and corrosion resistance, surpassing any other steel on the market. By exploiting a unique interplay between various alloying elements, Infinisteel exhibits remarkable properties that set it apart from conventional steel grades. The Infinisteel composition consists of iron 75%, carbon 1.2%, chromium 20%, vanadium 2.5%, molybdenum 0.8%, and tungsten 0.5%. So the biggest issue with this composition from ChatGPT is that it won't harden. When you heat treat knife steel, the main step is austenitizing. That's the high temperature step. So you heat it up hot and then you quench it. That's rapid cooling. So the heating up hot and quenching, that's how you harden steel. So in the austenitizing step, the high temperature step, you transform the steel from the low temperature phase of iron called ferrite to the high temperature austenite phase. And when you quench from austenite with carbon in it, you form martensite, and that's what makes hard knife steel. So if you don't form austenite, the steel doesn't harden because you have soft ferrite left in the steel. So why does this steel not harden from ChatGPT? Well, some elements are ferrite stabilizers, so they make ferrite more likely to appear depending on the temperature, and some are austenite stabilizers. And you need enough austenite stabilizers to counterbalance the ferrite stabilizers so that you can austenitize the steel. And in this case, this steel has a lot of ferrite stabilizers, chromium 20%, vanadium 2.5%, also moly and tungsten, while it doesn't have enough carbon for all of those ferrite stabilizers. So 1.2% isn't enough for all of those elements. And so when you heat it up, no matter how hot you heat it, you're still going to have ferrite present in the steel, so the steel won't harden. So overall, this steel really not good from ChatGPT. There are also some other weird things that it says in there. For one, it says that iron in the steel imparts strength and toughness to the alloy. Well, that's a very weird thing to say because all steel is made of iron. You're not adding iron, you're adding things to iron. Also, iron is pretty soft before we add other elements to it, especially carbon. So why would you say that iron imparts strength? So the AI is just saying things. It's not really adding anything. Another thing is it says that vanadium's primary function is to refine the steel's grain structure, leading to enhanced toughness and impact. So small additions of vanadium like 0.1, 0.2%, they are added to prevent grain growth. But in knife steels, when you're adding over 0.3%, in this case like 2.5%, that is for wear resistance because you're forming a lot of vanadium carbide, and those are very hard carbides that contribute to wear resistance. And in turn, they reduce toughness. So the AI is saying that vanadium is added for enhanced toughness, but it doesn't do that. It reduces the toughness. It also says that molybdenum was added for its resistance to high temperature creep and stress rupture. Well, high temperature creep is when a material is held under stress at relatively high temperature for long periods of time. So the material slowly deforms, which is called creep. So resisting creep is totally unnecessary in a knife. So the AI is just saying things that molybdenum does, even though it doesn't do anything for a knife steel. Another thing is it didn't list any manganese or silicon in the steel. These are not always added on data sheets, but they're present in all tool steels that I know of. I would just say that ChatGPT didn't mention them, but it also gave the percentage of iron as 75%, which means there's no more room left in a 100% alloy for manganese and silicon. So overall, this steel design, pretty bad. The person who sent me this composition also asked ChatGPT to compare it to MagnaCut. Somehow ChatGPT got the composition of MagnaCut wrong. MagnaCut has 10.7% chromium, but ChatGPT says it has 17%. I don't know how it got that wrong. It also said that MagnaCut has 0.3% nickel, even though nickel is not added to the steel. So I don't know where that came from. Also, it said that the higher vanadium in MagnaCut would make MagnaCut have higher toughness. But like I said earlier, more vanadium means more vanadium carbide for more wear resistance and less toughness. So this is not a reason why MagnaCut would have more toughness than Infinisteel. So overall, I give ChatGPT a D- for this really bad Infinisteel that won't harden.
This machine will tell us the precise location of the 3 remaining golden tickets. It says, I won't tell, that would be cheating.
Okay, on to the next one. So this person asked ChatGPT to create a unique composition of elements for a great blade steel that does not exist yet. ChatGPT said, creating a unique composition for great blade steel requires a deep understanding of metallurgy and the desired properties in the resulting steel. While this composition doesn't exist yet, we can propose an innovative blend of elements to produce an exceptional blade steel. Name Ultravium steel. Or maybe it's Ultravium. I don't know. The composition, 2.5% carbon, 7% vanadium, 3% molybdenum, 5% tungsten, 1.5% niobium, 2% cobalt, 0.5% copper, and 1% silicon. So ChatGPT started out by saying that creating a unique composition for knife steel requires a deep understanding of metallurgy. I agree totally with that. However, the composition that ChatGPT came up with does not have the required deep understanding of metallurgy, unfortunately. So the approach that ChatGPT took here appears to be just adding large amounts of every element. So this steel is a good example of how ChatGPT read things online. And if you look up what different elements do in a steel, almost all of them just list the positive things that different elements do. And so when a layman reads about the different elements, they think, why don't you just add a lot of every element? And ChatGPT has the same issue. And so it doesn't have any concept of trade-offs with elements. What are the negatives that happen with different elements, and how do you balance different elements together? ChatGPT has no idea. Though it says things like molybdenum helps maintain blade sharpness under high-stress conditions. I don't know what that means or how molybdenum is helping. Is a high-stress condition one where you're under attack, so you're under a lot of stress? Or is high stress meaning engineering stress, where a load is being applied to the knife? I don't know. It also says that tungsten is added to withstand extreme temperatures. What kind of temperatures? So normally knives are used at room temperature. So really hot for a knife would be like 100, 115 degrees maybe. So is this knife for use in volcanoes? So if so, that's probably more dangerous to the human than to the knife. It also says that niobium is for grain refinement. Earlier, ChatGPT said something similar about vanadium. But 1.5% niobium is way more than you need for grain refinement. That kind of amount is for wear resistance, and ChatGPT didn't even mention wear resistance as being a reason for adding niobium. So it also said cobalt was added for high temperature performance, which again, we don't need in a knife. Copper was added for a touch of corrosion resistance, according to ChatGPT, which also doesn't make much sense to me. Why do we need just a touch of copper for a touch of corrosion resistance? The big omission with this steel, though, is that there is no chromium added to it. ChatGPT didn't even mention chromium. So why is it going on to say that Ultravium steel is going to have excellent corrosion resistance when there is zero chromium? And chromium isn't only added for corrosion resistance. It's present in nearly all high alloy tool steels. It's added so you get high hardenability so that you can quench it slowly and still fully harden. So this is important because tool steels are usually quenched in air, like under pressurized nitrogen. And so if you don't have chromium, you're probably not going to have sufficient hardenability, and thus it'll be very difficult to heat treat the steel in an industrial environment. Then ChatGPT says about heat treatment that Ultravium steel would undergo a precise heat treatment process, including quenching and tempering to maximize its hardness, toughness, and fine grain structure. The ideal hardness level would be around 65 to 66 Rockwell. But, why? What is the precise heat treatment? Why 65 to 66 Rockwell? And, precise doesn't tell us that much. Why is it precise? Is every steel require a precise heat treatment, or does this steel in particular require high precision in its heat treatment? So my grade for this steel is C-, better than Infinisteel because it actually can be heat treated, but since it claims it has excellent corrosion resistance while not containing any chromium, it gets a C-.
I bring you peace. It may be the peace of plenty and content, or the peace of unburied death. The choice is yours. Obey me and live, or disobey and die.
The frightening story of the day man built himself out of existence.
Another one that was sent to me was someone asking for MagnaCut Plus, an improvement on MagnaCut. Now, of course, I designed MagnaCut, so maybe I'll be biased when I'm looking at the design from ChatGPT, but I will try my best. So the composition that ChatGPT gave for MagnaCut Plus is carbon 1.05%, chromium 11.5%, vanadium 3%, molybdenum 2%, tungsten 0.5%, nitrogen 0.3%, niobium 0.5%, and cobalt 1.5%. So ChatGPT gives some very strange reasoning for why this steel will be an improvement on MagnaCut. One is it says the increase in vanadium and tungsten would lead to harder vanadium and tungsten carbides, resulting in better edge retention. That is a very strange thing to say because MagnaCut Plus does not have more vanadium, it has less. So MagnaCut Plus is 3% vanadium and MagnaCut is 4%. So I don't know why ChatGPT thinks it has increased vanadium. Why is the AI unable to do this basic math comparison? It also claimed that it added tungsten to form tungsten carbides. In these types of high alloy steels, adding a tiny amount of tungsten does not lead to the formation of any carbides that are tungsten rich. The tungsten incorporates into other carbide types like vanadium rich carbides or chromium rich carbides, and those carbides would not be any harder by the tiny addition of tungsten. So a small addition of tungsten is not really going to lead to higher wear resistance. It also said that more niobium would aid in creating a finer grain structure. Well, the niobium content was reduced. It's 0.5% in MagnaCut Plus versus 2% in MagnaCut, so it does not have more niobium. So why does it think it has more niobium? I don't know. It also says the changes may require more precise heat treatment to unlock the full potential of the alloy. So again, ChatGPT is talking about precision in heat treatment. Why does it require more precise heat treatment? Based on what? I don't know why it's obsessed with precision. So other criticisms of this design require a bit more in-depth analysis with thermodynamic software that predict carbide types in alloy and solution. So this type of prediction is not based on any machine learning or AI, but it is very sophisticated software. So ChatGPT claims an improvement in corrosion resistance because of the higher chromium versus MagnaCut, the original. But there's also 3 to 5% chromium carbide in the final heat-treated structure, which reduces corrosion resistance. The main thing that led to an improvement in corrosion resistance with MagnaCut versus previous stainless steels was that the chromium carbide content was reduced down to 0 or near 0. And so that improved corrosion resistance. But that innovation was dropped by ChatGPT because ChatGPT doesn't know what it's doing. It doesn't know how to design knife steel. It doesn't even know how MagnaCut was designed. Also, the carbide content of MagnaCut Plus and MagnaCut is similar, which would give them roughly similar toughness. But MagnaCut Plus has half of its carbide as the larger chromium-rich type. And when you have larger carbides, that reduces toughness. So MagnaCut Plus would be unlikely to have higher toughness. ChatGPT also claimed that cobalt improves toughness, but cobalt does not improve toughness, so that would not lead to an improvement. So overall, I give this steel a C. It can be hardened, and it would be nearly stainless. But calling it MagnaCut Plus doesn't make sense because ChatGPT reduced corrosion resistance, it reduced wear resistance, and it reduced toughness relative to MagnaCut. So I don't know why you would put a plus on the end of MagnaCut with a design that is not an improvement. So it gets a C from me.
I think that what we're doing now is, in a sense, creating our own successors. We have seen the first crude beginnings of artificial intelligence. It doesn't really exist yet at any level because our most complex computers are still morons, high-speed morons, but still morons. Nevertheless, some of them are capable of learning, and we will one day be able to design systems that can go on improving themselves, so that at that stage we have the possibility of machines which can outpace their creators and therefore become more intelligent than us.
So after looking at those few examples, I did have more examples that people emailed me, but I don't want this video to go on forever. In none of the proposals that ChatGPT gave did it ever say that the steel should be made by powder metallurgy. The very high alloy content of these steels means they would be pretty bad if they were made with conventional steelmaking. Some of them may not even be possible to make with existing steelmaking, meaning they would crack when trying to forge them or roll them. And at the very least, they would not be an improvement on existing steels if they were not made with powder metallurgy. So for ChatGPT not to state explicitly that the steel should be made with powder metallurgy, I think is a big omission and is another sign of the lack of understanding that ChatGPT is having with how to design knife steels, which of course is not even really designing them. It's just putting elements down. So also, ChatGPT provided no real heat treating information. There were no temperatures given at all. ChatGPT did claim in a couple alloys that it needed a precise heat treatment, but it didn't give any specific information on what that even means. Does it have a narrower temperature range? Is that narrower temperature range for austenitizing? Does it require faster quenching? Does it have a more precise tempering temperature? What requires the precision in the steel? In one steel, it said it needed 65 to 66 Rockwell. But how did it land on that number? I don't know. And one of the steels couldn't be hardened at all. So overall, it seemed like ChatGPT did not really understand how heat treating works relative to a steel design. Also, as I've stated a couple times now, the approach ChatGPT seems to take is to add a lot of every element. It thinks that elements improve steel, so you add a lot of every element, and thus you have a new super steel. It has no real concept of balancing different elements together or what the drawbacks are for different elements. And so, this is kind of like what would happen if an internet expert tried to design their own knife steel. They would just add some of this and some of that and some of this to get all the properties they want and thus get a new super steel. But that's not how it works.
Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What's the problem?
I think you know what the problem is just as well as I do.
What are you talking about, Hal?
This mission is too important for me to allow you to jeopardize it.
I don't know what you're talking about, Hal.
I know that you and Frank were planning to disconnect me. And I'm afraid that's something I cannot allow to happen.
So ChatGPT is pretty terrible right now for developing knife steels, but it is a large language model. It was trained on huge amounts of written text from the internet from people. And it uses statistical information about how humans put words together to generate coherent text. However, the model as it stands is not good at collecting data about different things. It's not good at analyzing and comparing data. And it can't find any unique insights or solutions and turn that into information or a useful solution like a knife steel composition. The other problem is that the information it's gathering is just from stuff off the internet. And the internet is, in general, not a good place to learn about steel and metallurgy. Most of that is locked in journal articles and books. This is partly why I started Knife Steel Nerds, my website and blog, and then later the YouTube channel, so that I could get good information on the internet, because a lot of it is just written by lay people that don't know metallurgy, and they read other articles and they regurgitate information, and myths continue to perpetuate and misunderstandings perpetuate, and of course there's just a lack of understanding about the details. And so ChatGPT is a very general AI, but if we wanted to make something really good for designing knife steel, we would need a narrow AI, an AI designed just for designing steel, or more specifically knife steel or tool steel or stainless tool steel. So this is a classic example of garbage in, garbage out. When the information you're putting into this AI is not relevant or not good for designing knife steel, then it cannot design a good knife steel. However, there is another problem. We need a really good data set for putting into an AI for how to design knife steels, and I think that data set largely doesn't exist. A lot of information on tool steels and stainless steels are locked within specific steel companies or even inside the heads of individual metallurgists. The scientific literature, like journal articles and reported experiments, are not usually in a format that would be easily usable in a large database for an AI. Each study is done with different conditions. They hot rolled the steel differently. They tested different size coupons. They used a different type of test. They looked at the microstructure but not mechanical properties. They tested Izod toughness instead of Sharpie toughness. This all is really hard to put together. If you really wanted a great database for AI, you would want to look at the same types of data. You would want the same toughness data to compare between. Now, maybe an AI could make sense of some of this, but you really need a big data set for the AI to be able to pull from. And the more specific you could make that data set, the better the AI would be. Of course, a human looking at the same data set would also benefit from a better data set, but the better your data, the better the AI. For my own development of steel, I use a lot of different things. One are journal articles and books, which collect different studies to find trends with different variables, changes to composition and heat treatment, and etc. I also use my own data, which I've collected the last several years for knife steel nerds, toughness and corrosion resistance and hardness and edge retention. I've collected a lot of it for a whole range of different steels. Another is the thermodynamic software that I mentioned earlier. Again, this software does not use machine learning or AI, but it uses big databases of different steel compositions so that it can predict microstructure at different temperatures. And when this works perfectly, you can know what carbides you would have and what elements are in solution in the steel and how much at different temperatures. And you could use that information to generate steels that have the right matrix composition and the right carbide composition for the properties that you want to have. And then lastly, I use simple models for different properties. So with all of the different data that I've collected over the past several years, I have simple equations which predict properties like toughness and corrosion resistance and hardness, etc. Some of these come from journal articles and books, and some are simple regressions that I've created using my data. So I have older articles you can read on like studies of edge wear where we predict how well the steel will do in a Catra test based on its microstructure and its hardness. And I also did a study on corrosion resistance where we compared the matrix composition like chromium in solution versus a salt spray test. And you can make predictions about how different compositions will do in a corrosion test. So with those pieces of information, I can come up with approximate property targets and balance elements together. A similar process could be used for a narrow AI. You can even plug in existing thermodynamic software into a narrow AI, which has already been happening. It's becoming more and more common. And I think to do better than humans, we really need a bigger database of experimental data than we currently have. You might be able to make small tweaks to even existing steels, like smaller elements like molybdenum or silicon or manganese or nitrogen. You might be able to change them somewhat and have similar properties overall, but improve it in different ways. Currently, without experimentation, by making tons of variations, we don't always know what changes will lead to improvements. If our database of information was big enough, maybe an AI could help us narrow down the things to try, reduce the number of experiments, and thus come up with better ideas. But we are not there yet.
The Thinking Machine.
Hello again. With me tonight is Professor Jerome B. Wiesner, Director of the Research Laboratory of Electronics at MIT. Dr. Wiesner, what really worries me today is what's going to happen to us if machines can think. And what interests me specifically is, can they?
Well, that's a very hard question to answer. If you'd asked me that question just a few years ago, I'd have said it was very far-fetched. And today I just have to admit I don't really know. I suspect if you come back in 4 or 5 years, I'll say, sure, they really do think.
Well, if you're confused, Doctor, how do you think I feel?